And I would usually, I've already got most of your exams graded, but I've still got, I've got 3 more that have to be completed. That are kind of makeup exams, so I don't have all the data yet. However, the average is up, so that's a good thing. So far so good. Some of you improved. Most of you kind of broke even. Some of you came down a little bit. So if you've got any concerns, then come and see me. Unfortunately, I sent you on email. I've got kind of an emergency I have to deal with, so I will not be having office hours after 10 o'clock today, or not long after 10 o'clock. So if you need to talk to me today, you can talk to me after class. And we'll set something up. Okay, any questions? All right, so what we're going to do is we're going to talk about something that you've actually already heard about. Because I've brought this up in other contexts and quizzes and also in the class. But now we're going to officially talk about this. How many of you, is anybody taking differential equations? Okay. Did you see eigenvalues and eigenvectors there? Yes. And even if you don't see them, you see them because they kind of show up behind the scenes as well. The idea behind this, and I've actually, like I said, I can find this earlier in class, but let's kind of nail this down here. Let me kind of give you sort of an intro. When your transformations. Transformations sometimes right. Let me give you let me just give you some examples. What does this linear transformation do? That's basically it. It takes any vector and stretches it out twice its length, right? So, for example, so I can write this out in the matrix, you know, and feel all good myself because I'm being fancy and all. But effectively, what have I done? What has this done to the input vector xy? Double it. That's it, right? Just multiply it by 2. So multiplying, so basically multiplying any vector by this matrix here is effectively just multiplying by the scalar 2. What about this? Here's another example. Let me call this example. This doesn't double effect necessarily, right? Because if you look at if you look at 2, 0, 0, 1 times xy, this is 2x y. Everybody agree with that? And this isn't actually multiplying the vector by anything. Well, except in one special case. Right? Well, some special case. This isn't the original vector times one single number, right? Necessarily. Well, let me point out that this particular vector is double, right? Everybody agree with it? And this particular vector here It's just multiplied by 1. Right? And sometimes it can be more hidden than that. Notice, first linear transformation basically just doubling. I mean, this linear transformation is just doubling stuff. This linear transformation isn't just doubling stuff, but I noticed that if you have a vector like this, where in fact you need some scalar multiply of it, it just doubles it. If you have a vector like this, it just leaves it alone, right? So this brings us to that. An eigenvector say B A, but this can be anything, by the way. Let me point out, when I'm talking about eigenvectors, eigenvalues, I am talking about square matrices. So this is a square matrix. Is a non-zero actually some eigenvectors can be 0 and following. Since I made the definition eigenvectors non-zero, I'll explain why I do that here. This is a non-zero vector V such that A, B, and B, some scalar. So some number lambda. A scalar lambda is an eigenvalue if there is a non-zero vector B such that A, B, and let me say if A, B equals lambda B, we call lambda B an eigenvalue. We call it AB lambda B eigenvalue. So, for example, let's go back to this. T of this vector is twice this vector. That means any vector is an eigenvector for the eigenvalue 2. So 2, any vector you like, is an eigenvalue eigenvector pair. In this example right here, 1, 0 is an eigenvector corresponding to the eigenvalue 2. So 2 and 1, 0, eigenvalue eigenvector pair. For the same matrix, 0, 1 is an eigenvector for the eigenvalue 1. Everybody okay? Let me point out. If B is the 0 vector, because remember I said it's non-zero. If B is the 0 vector, then AB equals lambda B works for any lambda. Everybody agree with that? If I put the 0 vector in here, it doesn't matter what lambda is, that equation is balanced, right? And that's why we specify this is non-zero, because otherwise you kind of get garbage out of it. It turns out that 0 actually has to be an eigenvector. We have these things called eigenspaces, But in the definition, I'm going to treat like it's non-zero because there's ambiguity with these. Okay, any questions so far? Okay, so let's, I want to do a bunch of things. Let's see if we can find all possible eigenvalues. Eigenvector. You have any non-zero eigenvector. Well, this is simple enough where I can kind of solve this. It's a little too bad. Right. And actually, I want to get here. I'm actually going to cover a little bit, talk a little bit more stuff than is actually in your section here. I'm going to give you the symmetric theorems as we go along. But let's just try to do this. So let's write down what our players are. Well, players are A is 0, 1 minus 1, 0. And B, I'm going to let this be x, y. And lambda stars itself. Lambda is just 10. Right? So let's see what we get. Let's just see. Well, I don't know much, but I do know how to multiply this matrix times this vector here. And this is going to be y minus x everybody agree with that? So let's just do what comes naturally and set them equal so that happens. Now, I do see one solution. So let's see, and it's a rather silly solution. Anybody see it? What you say? Okay. If lambda is 0, you let lambda equal 0, then you get y is 0 and x is 0. Now tell me why I want to throw that one in the garbage. Yes.
Because by definition, it can't be 0.
Right. If lambda is 0, that means my y part of the vector is 0 and my x part of the vector is 0. And I said I wanted a non-zero item, right? Okay. So let's suppose, let me kind of summarize this. Lambda equals 0 and b is 0 vector. So I don't want that. So let's suppose lambda's not 0. Right? And the cool thing about that is it means I convert it. So since also v is not 0, one of either x or y has to be not 0, right? Because they're both 0, and that's 0 vector. So let's suppose first And let's do this right here. I'm going to take this equation and I am going to plug in y equals 1 to x here. Now, x is not 0, so what can I do? Yes,
Divide by x.
divide by x. And I do that. Everybody agree? What does the eigenvalue have to be then? It has to be I or negative I, right? And that's not a real number. So this actually, if you want to restrict yourself to real matrices, this is impossible, right? Everybody agree with that? And let me point out that if you, on the other hand, assume that y is not 0, you did basically the same thing with lambda has to be I. So this actually has no eigenvalues. And by the way, can anybody describe what this transformation does? It takes xy and turns it into y minus x. Everybody smooth? Yeah. Yes.
This is like a 270-degree revolution. With like a vector
Which way are you going?
counterclockwise, 270.
I don't remember. Let's see. What happens to, here's how I can remember.
Oh, wait, now.
Where does 1, 0 go? It goes to, well, let's see, x is 1, y is 0. That goes to 0 minus 1. And where does 0, 1 go? Now x is 0 and y is 1. That goes to 1, 0. That actually goes here. Looks like that's 90 degrees clockwise.
Everybody agree with it? Is that the same as 270 counterclockwise?
Yes, it is. So you would do it. So can somebody explain, man? So seeing algebraically, I get this mess here. I couldn't solve for lambda. I couldn't solve for a real one. Can somebody explain to me why this thing has no eigenvectors? So we call it B. What does it mean to be an eigenvector and an eigenvalue? It means the linear transformation just stretches it or contracts it. Maybe turns it 180 degrees, but that's negative, right? But does this ever happen? Any vector, no matter where you are, you go 90 degrees clockwise. It is never a stretch to go 90 degrees clockwise. Never a stretch. That's it. Everybody agree with that? Except there's one silly vector that sort of is a stretch. What vector is that? The 0 vector, the one that just sits here and spins, right? I mean, that one's a stretch for the first. So there's geometrically, this has no eigenvectors because everything's spinning and there's nothing being stretched. Okay. Let's do some other examples, but keep that one in mind. So I'm going to jump back on this example. Suppose suppose that lambda p is eigenvalue, eigenvector pair. Or so that is to say, and suppose we have an eigenvalue here, the collection of all vectors such that so let me point out that if you have a non-zero vector b and ab lambda b, well, okay, that works, but also b equals 0 works. Somebody agree with that? B equals 0 will always bounce. If you look at every single distinct vector that balances this equation, then this collection is the substance of R, where here A is an invariant equals. So the vector term in high. This collection is a substance. It's called eigenspace. The collection of all vectors that satisfy this is called eigenspace. See if you can figure out, it's a good exercise. I've already shown you the zeros in there, right? Because 0 balances that equation. See, so suppose you have two vectors, v1 and v2, that balance that equation. Show that v1 plus v2 does, and show that the scale of multiple balances that equation. So here's an example. Let's take as it turns out, two how do you know that? Because I figured it out before class. How do you know that? Well, I'm going to show you how to do that later, but for right now, you can just kind of take it on faith. So we're in like a late session of church here, and I have a little faith and believe that 2 is in fact an eigenvalue, and then I'm going to show you how to do this later. What I want to do is armed with this knowledge, I want to find eigenvalues. Okay. Now, what I'm going to do here, be an example, I'm going to show you kind of a general approach. So you're looking for all x. Let's say correct. Because here my eigenvalue is 2, right? So I'm looking for every vector such that ax equals 2x, right? This is not convenient. I'm going to couch this to something that's more familiar to us when you're out. Now watch this, nothing up my sleeve. And just 0 vector. And I'm going to slip something else past you here too. This is just so I can pull something out later. By this, I mean the 2 by 2 identity vectors, right? Everybody okay with it? Because X, vector X is the same thing as X times 2 by 2 identity vectors. This allows me to pull the X out. And this is a familiar concept. Can anybody tell me what? When we're trying to find all X such that AX equals 2X, that's the same thing as finding all X that this is true. So what are we doing? We are finding, can somebody describe what all X such that A minus 2 I2 X equals 0? What is that? Yes.
We're just taking the matrix A and subtracting 2 to the diagonal elements. And doing just finding the homogeneous.
Okay, there you go. You're finding the solution to the homogeneous. You're finding the null space of the matrix A minus 2 I2, right? This is finding the null space. And more generally, finding, if you know the eigenvalues, more generally, what you do is find the null space. Find the null space of this. And this is an old familiar song and dance. So let's do this. Let's find null spaces. So what is that going to be? That's going to be minus 4, minus 2, 6, 3. Can somebody tell me why they? Can somebody put your eyeballs on that and tell me real quick why? Yes, indeed, I know this has a non-trivial null space. Yeah.
Let's look at each other. So let's
That's right. Determine zero as well as multiple. So I know for sure there's going to be a non-trivial null space. That's going to be lurking. Let me ask you this: what conclusion would you come to if the null space was trivial? Right. So what that would mean is the eigenvalue I picked only has a trivial solution, which means it's not a true eigenvalue. Right? Well, let's do this thing. Let's see. Right, I'm just going to go on the biggest thing. I reduced that one quick. Everybody okay with that? So x2 is free. And I have x1 plus 1/2 x2 is 0. So that means x1. So for the eigenvalue 2, well, for the eigenvalue 2, I get the following eigenvector x1, which is minus 1/2 x2. I don't like that fraction, so you know what I mean, I want to put x2 with a chapeau on it, 1 negative 2. What did I do there? I multiply by -2, and it doesn't really matter, right? Because this constant can be anything. Right, right? By the way, let's check. What happens if you look at A times 1 minus 2? This is -2, -2, 6, 5, times 1 minus 2. And this turns out to be -2 plus 4 is 2. That's going to be 6 minus 10 is -4. Notice that it's taking the spectrum and multiplied it by 2. So it is an eigenvector for that eigenvalue.
Why do you denote it with an at?
Because it's not the same x2 that I wrote down before. I didn't know that. Because this x2 should be like I guess half the other one. Right? Okay, how about a big one? Suppose. So I'm going to tell you this just flat out. Eigenvalues. What is this matrix? 6, 1, minus 2, 0, minus. By the way, I'm going to pull this theorem in later, but what it means to be an eigenvalue is when you subtract that element off the diagonal, you get a matrix that has a non-trivial null space, right? Look at this matrix here. Does anybody notice anything about it? What's the determinant of this? 0. A lot of people are saying 0. How do you know that? Right. This row is -2 times the bottom row. So determine this to 0. What are my eigenvalues? That means that I don't have to do anything to it to give it a non-trivial null space, right? And in fact, that's a theorem that I'm going to report later. Is a matrix is singular if and only if it has 0 as one of its eigenvalues. Right? So let's explore this. So let's find the eigenspace of both of these. Lambda equals 0. Let's find the null space of this thing. Okay, everybody agreed this bottom row can kill this top row, right? So I'm going to do a lot of moving around. I'm going to put the middle row on the top, 1, 1, 2. I am going to put this one here with the sign change, and this row comes to 0. So I did a lot of moving around there. Are you all comfortable with that? Now, multiply by -2. And add downstairs. 2, 2, right? And actually, I'm going to work this into relative stationary form. And I'm back. And one final step. Relative stationary form. So What is the dimension of my eigenspace? One. It's the same thing as the dimension of null space. Ask yourself this: self, how many free variables are this? One. So that's the dimension. All right. So I need the equation x1 plus 3 halves, x3, 0, and x2 is 1 half x2. 0. So a typical element of my eigenspace looks like x1, x2, x3, which is minus 3 halves, minus 1 half, and so or I could also do minus 3 minus 22 or whatever I would find it effective. So the eigenspace is one dimensional and it's measured by this. What about the eigenspace for 1? Let's run that through the opera and see what happens. I mean, eigenspace for this. Well, what we have to have now is A minus 1 times I3 upon null space. So we subtract 1 off the diagonal here. It's 3 over 6. 1 over 2 and minus 2, 0 minus 4. And this one's, oh yeah, this one's Jim's big party machine here, because what's true about this one? All the rows are multiples of that. The most convenient one, I think, is the middle one. So let's look at this. These other 2 rows are multiples, so yes. Okay, now how many free variables you got? Now we've got 2, so I expect my eigenspace now, the equivalent of null space of this, to have 2 dimensions. So I have 2 linearly independent eigenvectors. Let's see how this pans out. X2 and X3 are free. And I need the equation x1 plus 2x3 was equal to 0. So my typical eigenvector looks like this. See, x2 and x3 are both free. And x1 is what, negative 2x3? So actually, I see it's 2 dimensions. I've got 2 independent parameters. Now I've got a big eigenspace. It's 2 dimensional. It's generated by those 2 linearly independent vectors 0, 1, 0 and negative 2, 0, 1. Okay. Any questions on that? Yes.
That means that other eigenvector is in the combination of those 2.
Yes. Any linear combination of those 2 is an eigenvector corresponding to the eigenvalue 1. Right. So if you take any linear combination of this and you multiply the original matrix by that, it'll leave it alone. Right? Because matrix times linear combination is 1 times linear combination. So it leaves it alone. Okay. y'all so I can compare them. This is how, actually, some importance, and we're going to build this up later when we talk about diagonalization, but, if V1, V2, are eigenvectors corresponding to the state is important eigenvalues, random 1, random 2, random n. So what I mean by the state is all these numbers here, all these eigenvalues, they're all different. Then this set of eigenvectors right. So for example, in the previous example, we had an eigenvalue 0, and we had some vector corresponding eigenvector corresponding that. We had eigenvalue 1. We actually have these two different vectors. If you take the original vector for 0 from this vector, it's a linearly independent set. If you take the original vector for 0 in this one, it's a linearly independent set. So why is this? So I'm going to give you a quick pretty fast. If the set is not linearly independent, there is a smallest into K such that the K plus one of those vectors is a linear combination of the rest. Right. So, for example, I know that K has to be. Notice that V1 by itself is not the 0 vector, right? And so there has to be a smallest one of these, such the next vector is linear combination preceding vectors. If it's not a linearly independent set, let me point out that since K is the smallest, such that the next one is linear combination of preceding, that means that these have to be linearly independent, right? This is now a linearly independent set. Because if it weren't linearly independent, one of these would be a linear combination, right? So we're good to go on that. So let's say that A1 B1 plus A2 B2 plus AK BK is equal to B3 plus B. And recall that A BI equals lambda I BI, right? Because all these BIs are eigenvectors for A. So if you multiply by A, this is what I get when I multiply both sides of this equation by A, and I distributed the capital A out because it's matrix, and I can do that. And so let's see what I get. I get A1, lambda 1, B1, plus A2, lambda 2, B two. AK, lambda K, BK equals lambda K plus one. Right, so every one of this is lambda one V1, this is lambda two V2, lambda K BK, and finally lambda K plus one. Now, I am also going to take this equation here and I'm going to multiply it by lambda K plus one, giving me A1 lambda K plus one, A2 lambda K plus one, AK lambda K plus one, lambda K plus one. So my strategy is, the first thing I did is I multiplied this by A on both sides, and that gave me a tail end of lambda K plus one B. And then I said, hey, you know what, I can also multiply, just multiply lambda K plus one through, and I get matching ends. So if I subtract this, so subtract these equations, I get A1 times lambda 1 minus lambda K plus 1, A1 plus A2, lambda 2 minus lambda K plus 1, A2 plus AK, lambda K minus lambda K plus 1, AK is equal to 0, right? This side goes away. But this set of vectors is linearly independent. Right? So that means that one of these coefficients has to be 0. I'm sorry, that means all of it. That means all of it. So each AI each one of those coefficients has to be 0. All of them. And sum AI is not equal to 0. Because we have BK plus 1 is a linear combination of these things, and so one of these has to be non-zero. So for that value of I, and I get lambda I, lambda K plus 1, and this is impossible. Because we've already said that all the different lambdas are different. That's the problem there. Okay, so I've got kind of a question for you all here. How did I get these eigenvalues? So, yeah, I am done. Eigenvalue will be. So, right? I mean, basically, this is what we did earlier. We were like finding null space, ray minus lambda I. And this actually helps us find what lambda is. Right? When you have an eigenvector that's not 0, if this is not 0, then that means the null space of this matrix is non-trivial. Everybody agree? And that's a square matrix. When you have a square matrix and the null space is not trivial, what can you say about the determinant? The determinant must be 0. If B is not 0, then we must conclude the determinant of A minus lambda I is equal to 0. You can use this. This finds appropriate values. So for example, this is the first example matrix I did here. We call this A. Look at A minus lambda I, which is -2 minus lambda, -2, 6, 5 minus lambda. So take the determinant of this, set it to 0 and solve the lambda, and that will give you the eigenvalues. You can check all the matrices that I gave you today and figure out what the eigenvalues are. And in fact, this gives also that if a matrix has eigenvalue 0, it's singular. And here's another thing, you can look in your book for this, we'll talk about it next time. If you have a triangular matrix, either upper or lower triangular, the elements on the diagonal are the eigenvalues. Okay, any questions? Okay, there will be, I'm not going to give you a quiz over the weekend. You guys have a good weekend. I'm sorry about office hours today. If you've got concerns, can talk to me right now. Other than that, y'all have a good weekend. I'll see you on